अभी के शरीर भाई था
the last class we started looking at different characteristics of underdamped system. We said the underdamped system is going to have a oscillatory behavior, isn't it? And then we have looked at several definitions like overshoot, decay ratio. In the last class, we started looking at some of the definitions like overshoot, decay ratio. Then we have seen period of oscillation, rise time, response time. Then it is different definitions which we have seen in the last class. Also, we have looked at the derivation. So we said that the overshoot will be given by exponential of minus beta pi divided by under root 1 minus beta square. And overshoot is nothing but what? Overshoot is nothing but the ratio of A by B, isn't it? That is what we have defined. Then the next definition was decay ratio. Decay ratio we said the ratio of C by A. That is what we have defined as a decay ratio. It is nothing but the ratio of how much the response is overshooting above the ultimate value, and the ratio of that with two subsequent peaks, that is what we have called as decay ratio. Okay. So decay ratio comes out to be exponential of minus 2 beta pi divided by under root 1 minus beta square. So that comes out to be overshoot square. Then we have started looking at period of oscillation. So remember in the second order system we said this is what the response we are expected to get. Isn't it? Second order underdamped. So the response is given as Kp into 1 minus e raised to the power minus beta t by tau into 1 upon under root 1 minus beta square sin omega t plus phi, where omega is given as omega, which is nothing but radial frequency, which is given as under root 1 minus beta square by tau, whereas phi is given as tan inverse of under root 1 minus beta square by beta, isn't it? So this particular expression we have used here again. So radial frequency is given as under root 1 minus beta square by tau, isn't it? Correct. And the frequency f will be given by what? 2 omega is given as 2 pi f, isn't it? So f will be given as omega by 2 pi, correct. So based on that we can find out f, and 1 by f is nothing but t. So t comes out to be 2 pi tau divided by under root 1 minus beta square. And when we look at the natural period of oscillation, in a natural period of oscillation this beta value becomes 0. So actually we get the natural period of oscillation Tm comes out to be 2 pi tau, correct. So you can see that the natural period of oscillation is related with the time constant of the process. So unlike the first order process, the physical significance of the time constant of the second order process is nothing but natural period of oscillation. Okay, correct. Then response time and rise time. So response time is the time when your response comes within plus or minus 5% of the ultimate response. That is the time which we call it as a response time, isn't it? So response time is nothing but the time when your response comes within the plus or minus 5% of the ultimate response. And rise time is the time when your response reaches to the ultimate response for the first time, isn't it? That is rise time. Then we started looking at the derivation of each of these definitions which we have seen, like overshoot, decay ratio, etc. Isn't it? So we said that overshoot actually is nothing but what? Overshoot is nothing but, if you look at the overshoot is actually at the point here where we are having the peaks, isn't it? So we wanted to find out the time at which these peaks are occurring, isn't it? So how we can find out? We can take the response of the second order system and we can differentiate with respect to time and equal to 0, we will get the locations of the peaks as well as values. Okay, so that is what we have done. So here this is the usual response of the second order system, second order underdamped system, when the step input is given. When the step input is given, isn't it? So yt by kp, if I take it, yt is given as kp 1 minus 1 upon under root 1 minus zeta square e raised to the power minus zeta t by tau sin omega t plus phi, where omega is given as under root 1 minus zeta square by tau, and phase angle phi is given as tan inverse of under root 1 minus zeta square by zeta. So now in this case, again this yt is given by this another expression. Both these expressions are actually same. Here this sin and cos term are combined here. Both these expressions are same. Okay. So now we can take this particular expression and we can differentiate this yt with respect to t and then equate to 0. So what we are going to get? If we do that, we get this particular expression. 1 minus under root 1 minus zeta square by zeta, that comes out to be tan omega t plus phi. Whereas 1 minus zeta square by zeta is nothing but what? Tan phi. If you put tan phi here, so that expression becomes tan phi is equal to tan omega t plus phi. Isn't it? And both these right hand side and the left hand side can become equal only if omega t is equal to n pi. So that is why we are writing this omega t equals to n pi. So that gives me the locations of different peaks and valleys. Isn't it? So t comes out to be n pi by omega. Isn't it? Where n is varying as 0, 1, 2, etc. So you can see that when I am having n equals to 0, I am getting this value here. But when n is equals to 1, I get this peak. When n is equals to 2, then I get this value. When n is equals to 3, I get peak. So you can see that for all the odd numbers we get peaks and for all the even numbers we get values. Okay, isn't it? So with this then we can find out the expression of overshoot. So for overshoot what we have done is, once we have obtained the time which is given as n pi by omega, we can put this n equals to 1 here, so we get t equals to pi by omega. So when t equals to pi by omega, we get first peak, isn't it? So t equals to pi by omega we can put in this equation and we can simplify. So that is what we have done. In this expression we have put pi by omega, t equals to pi by omega. So with that, the simplification, if we do everything comes, if we simplify, what we get is yt by kp as n equals to 1, we get 1 plus exponential of minus zeta pi divided by under root 1 minus zeta square. But this y value, this yt by kp value is nothing but what? This is nothing but b plus a. And b is already 1. Isn't it? So a I can calculate. And that a comes out to be exponential of minus zeta pi divided by under root 1 minus zeta square. So that is nothing but the value of a. Isn't it? And a by b is overshoot. But b is already 1 in this case. So a by b is nothing but just what? Just a itself. Isn't it? So that's why overshoot we get directly as exponential of minus zeta pi divided by under root 1 minus zeta. So this is the expression of overshoot. Correct. Similarly, for decay ratio we put n equals to 3. For decay ratio we put n equals to 3. So what we are getting? We are getting the location of the third peak. We are getting the location of this third peak. This second peak we are getting, isn't it? Second peak we are getting, so that is at n equals to 3. Remember n equals to 0 here, n equals to 1 here, n equals to 2 here, and n equals to 3 at the second peak here. Correct. So again we can obtain the value of yt by kp here. So yt by kp comes out to be yt by kp for n equals to 3, that comes out to be minus 3 zeta pi divided by under root 1 minus zeta. That is what we are getting, isn't it? Correct. So that is the value we are getting as C. And C by A is nothing but the decay ratio. So this is C. This C divided by this A, that gives me decay ratio. That is what we have obtained, exponential of minus 3 zeta pi divided by under root 1 minus zeta square divided by A, which is exponential of minus zeta pi divided by 1 minus under root 1 minus zeta square. So this simplifies and what we get is exponential of minus 2 zeta pi divided by under root 1 minus zeta square. So this derivation is not there in your book. Please look at it carefully. Okay, and only the book is allowed in the examination, not the notes. Okay, notes given to you only for reference and for you to study. These are not allowed in the examination. Please don't bring the Xerox copy which I have put in the scoop. Only the book, hard copy of the book is allowed in the examination. Okay. If you are not able to purchase it from the shops, then take the Xerox. Take the Xerox of the book, but that Xerox should be hard binded. If I see the loose binded Xerox, I will not allow. Okay. Only the hard binded Xerox I will allow. Okay. Is it clear? So we can obtain this as overshoot square. So this expression is nothing but what? Overshoot square. So that is what the decay ratio we are getting. Again we can obtain the rise time. So rise time. So see, rise time in this case we have defined is what? This is the rise time. So rise time is the time at which the response becomes equal to 1. Isn't it? Correct. So in this case the expression of yt by kp we already know. Yt by kp, this is the expression for yt by kp, and we can equate this expression equals to 1. If we equate, then this 1 will get cancelled out with this, so we will get 0 on the right hand side, and if we put that, we get sin omega t plus phi equals to 0. Sin omega t plus phi equals to 0, that is what you are going to get for rise time. And from this you can obtain what is the value of omega t. So remember, sin omega t plus phi can become 0 only if omega t plus phi becomes n pi. Isn't it? So if you put omega t plus phi equals to n pi, we can find out what is the t here. So t comes out to be n pi minus phi divided by omega. Note down here that for rise time this n equals to 1, not 0. Remember, n here can vary 0, 1, 2, 3, 4, etc. If you put 0, then you will get a rise time in negative, which is not feasible. Isn't it? So in this case, n you have to use equals to 1. If you put n equals to 1, then you get the rise time here. So rise time comes out to be t tau divided by under root 1 minus zeta square into n pi minus pi. Okay. Is it clear? So in this case, if you put n equals to 0, what you are going to get? If you put n equals to 0, then you are going to get the rise time which is negative. So if you look at physically what it means, so you will get a rise time over here. It is not visible. Isn't it? It is not visible because you have given the step input at time t equals to 0. How can you get a rise time in the negative direction? It is not visible. So in this case, n has to be used as 1. If you use the n equals to 1 corresponding to this, isn't it? Then you get the rise time somewhere here. Isn't it? So n should be equal to 1 in this case. Is it clear? Definition? इसके कुछ confusion? So rise time definition is what? Rise time definition is, this is the time. The rise time is defined as the time required for the response to reach its final value for the first time. For the first time, isn't it? So if I look at this particular figure, this is not a rise time. This is also not a rise time. Rise time is only this. When you are reaching the ultimate response for the first time. Okay, that is the rise. Negative time नहीं आ सकता ना time. How can the time rise time can be negative here? Because step input itself we have given a time equal to 0. Okay. So see. When you find out the roots, very often we get the quadratic equation, and when we find out the roots, sometimes we get the negative roots, and we say for a physical system the roots are not negative, then we discard that. We have done that from our school days. Same thing is here. If you get a negative value, that is not possible physically. Mathematically you are getting it. Isn't it? That's not the problem. But physically, having the rise time in negative is not going to be there. Why? Because you have given the disturbance to the system at time t equals to 0, isn't it? So the system is going to respond to that disturbance only in the positive time, isn't it? So if you are calculating the rise time in a negative direction, it has no meaning, isn't it? So the rise time in this case you have to find out by putting n equals to 1 and not n equals to 0. N equals to 0. Okay. Clear? आराम से दिन में क्यों सोते हो? रात में सोया करो. Why you have become nocturnal? कितने बजे सोते हो इस राशि? हाँ बताओ कितने बजे सोते हो? 5 बजे सवेरे. चलो बताओ राइस टाइम क्या है? अभी तुमसे राइस टाइम पे शुरुआत करते हैं. बताओ, चलो खड़े हो जाओ. खड़े होके बताओ राइस टाइम क्या है? बताओ खड़े हो जाओ. आपको अपने दोस्तों को बताना है राइस टाइम. बताओ. नहीं यही बताइए. खड़े हो जाओ. व्हाट इज राइस टाइम? और कौन कौन सो रहा है यहाँ? हाँ बताओ राइस टाइम क्या है? अरे अभी तो बताया 2 मिनट पहले. आप बताओ रिस्पॉन्स टाइम क्या है? चलो खड़े हो जाओ. याद नहीं होता. अच्छा आप ही खड़े हो जाओ. आप बताओ ओवरशूट क्या है? अभी तो 2 मिनट पहले डिस्कस करे हैं. अब से जो भी बात करते हुए, जो भी सोते हुए पाया जाएगा उसको इस तरीके से खड़ा करेंगे. और किसी को आ रही नहीं आ रही? बताओ बेटा. आप बता ही नहीं रहे हो कैसे आगे नहीं बढ़ेगी उसके बिना. आपको बता रही है कि क्लास को पूरा तभी आगे बढ़ेगी. तो अगर आप सोओगे तो देन दिस इज राइज टाइम इज टाइम टू राइज. इसलिए आप खड़े हैं. ठीक है, आप इसलिए खड़े हो गए क्योंकि ये टाइम था राइज होने का, है ना. तो अभी आप अपनी नींद से राइज होकर थोड़े खड़े हो जाओ. हाँ यहाँ से बताओ. यहाँ से नहीं. हाँ यहाँ से भी बता सकते हो. राइज टाइम लिखा हुआ है. इस वाली फिगर में बता दो. चलो अंडर डैम से. अंडर डैम से तुम यहाँ बता दो. मतलब तुम ही सो रहे थे तो गलत पे कैसे कर लिए? गलत पे कर लिए. चलो एक बार बताओ अंडर डैम क्या है? तुम बताओ. मैं देखते कितना लोग पता है. लेट अस सी कि हाउ मेनी पीपल नो अंडर डैम. बताओ चलो क्या है अंडर डैम? अंडर डैम सिस्टम क्या है? आप बताओ बेटा ओवर डैम क्या है? खड़े हो जाओ, खड़े हो जाओ। सबको टेस्ट करना है। बताओ और डैम क्या? आप किताब छोड़ दो बेटा, किताब छोड़ के बताओ क्रिटिकली डैम क्या है। आप खड़े हो जाओ। क्रिटिकली डैम क्या है? क्रिटिकली डैम क्या है बताओ? पीरियड ऑफ ऑसिलेशन क्या है आप बताओ, खड़े हो जाओ। नेचुरल पीरियड ऑफ ऑसिलेशन क्या है या जस्ट पीरियड ऑफ ऑसिलेशन? This is I am opener to me. Only I am getting things. बाकी सब लोग सो रहे हैं। खड़े हो जाओ, आप बताओ पीरियड ऑफ ऑसिलेशन क्या है? आप देख रहे हो ना, अब बताओ पीरियड ऑफ ऑसिलेशन क्या है? गुड, वेरी गुड, ठीक। So what is the O-dam system? Anyone? O-dam system क्या है? When zeta is greater than 1. समझ में आया? When zeta is greater than 1. What is zeta? Damping factor. Damping factor is greater than 1. Then the system is over-damped. आपको क्या पूछा था बेटा? अंडर-डैम्प सिस्टम क्या है? तो आप बताओ क्या होगा अंडर-डैम्प? आपको ओवर-डैम्प पूछा था क्या? अच्छा, अंडर-डैम्प बताओ। When zeta is less than 1, then it is under-damped. Critically damped क्या है? Equal to 1. कैसे यही ऑप्शन बचाएगा? ठीक है। अब नेचुरल पीरियड ऑफ ऑसिलेशन बताओ। नेचुरल पीरियड ऑफ ऑसिलेशन क्या है? आपका अंडर-डैम्प नहीं, चेंज हो गया। नेचुरल पीरियड ऑफ ऑसिलेशन बताओ क्या है? एक ऑसिलेशन के लिए जितना वो नेचुरल पीरियड ऑफ ऑसिलेशन नहीं है मेरे दोस्त, वो केवल पीरियड ऑफ ऑसिलेशन है जो उन्होंने बताया। नेचुरल पीरियड ऑफ ऑसिलेशन बताओ क्या है? Anyone? What is natural period of oscillation?
Sir, when theta equal to 0, the time period.
When theta equals to 0, then
The time
period of oscillation, that is called as natural period. समझ में आया? When theta is 0, then you calculate the period of oscillation. That is natural period of oscillation. ठीक है? Rise time. Rise time बताओ। क्या है rise time? Time to rise in the morning. Rise time क्या है? What is rise time? Anyone? First time? When the response reaches to ultimate response for the first time, that time is called as rise time. ठीक है? Response time पूछा था आपको, बताओ response time क्या है? नहीं। What is response time? Anyone?
Ultimate time का 5% plus minus.
समझ गए? Overshoot क्या है? Overshoot. What is overshoot? The value by which बताओ। Desired value divided by the accuracy. B by A is B over. Okay. ठीक है, ठीक है, सॉरी ये बात चलो बैठ जाओ, अभी बात से सोना नहीं है क्लास में, ठीक है बैठ जाओ। अच्छा ओके, तो वेयर वी आर, so now we just wanted to summarize what we have seen so far. Okay, so whenever we give a step input to the system, when we give a step input to the system, then how first order system is going to respond, how second order system is going to respond. Again in second order there are three cases: overdamp, underdamp and critically damped. So you can see that if you give a step input at time t equals to 0, my first order response is this. My first order response is like this. But if you look at the second order system, the response of the second order system is sigmoidal. Unlike this, the response of the second order system is sigmoidal. You can see that the response of the second order underdamp is faster, but then it also associated with the oscillation. Critically damped is slightly faster compared to overdamp. There is no oscillation. Overdamp system is sluggish and delayed compared to critically damped. Isn't it? So if you compare all these plots in one representation, you can see here, this is first order process, this is second order system, isn't it? Again, if you increase the order of the system, your system response is going to become more and more sluggish and delayed, isn't it? So you can see this is third order system, then fourth order system. As the order of the system increases, your system response is going to become more and more slow. Now, where this is important? This is important in every chemical engineering application. For instance, if you are looking at, let's say, distillation column, if there is a change in the inlet feed rate, remember feed you are giving in a in between feed rate, isn't it? But ultimately you are interested in how this change in the feed rate is actually impacting your quality of the distillate. So between the feed tray and distillate, let's say there are 20 trays in between. So these are 20 first order processes in series, isn't it? So more number of trays are there in between, higher is the order of the system, and your system response is going to be more and more sluggish and delayed, isn't it? Correct? And mostly in chemical engineering you see all these separation equipments are primarily stage-wise operations, isn't it? Like if you look at the absorption column or distillation column, usually you have different trays, isn't it? Correct? So this is what you see in distillation column as well as absorption column. Okay? Alright? Now let's start with the first illustration here. So we wanted to look at, so far we were only understanding the concept of the second order system, isn't it? Now we are trying to understand this concept in the context of equipment. So here we are looking at two tanks in series, isn't it? They are arranged in two ways. In first arrangement, both these tanks are arranged in a non-interacting manner, and in the second case, both the tanks are arranged in a interacting manner. This same experiment you are going to perform next year in the process control lab. Okay, interacting and non-interacting tanks. Okay, so in this case you can see that this particular arrangement we are calling it as a non-interacting system primarily because here you can see that the outlet flow rate from the tank 1 depends on H1, isn't it? And that is given as an input to the second tank, isn't it? So you can see that the dynamics of the second tank depends on the dynamics of the first tank, but reverse is not true. Reverse is not true. But if you look at the second case, in this particular case, this flow rate depends on how much is the change in the height of the tank 1 and tank 2. So here this flow rate is proportional to H1 minus H2. So you can see that dynamics of the tank 1 is impacting tank 2 and vice versa is also true here. Dynamics of the first tank is also dependent on the dynamics of the second tank. And that is why this system is called as interacting system, whereas this system is referred as non-interacting system. Okay. So here you can see this dynamic is not dependent on this. Here dynamics of this first tank is also dependent on the dynamics of the second tank. That is the difference. Is it clear to everyone? Interacting and non-interacting tanks. Now, whenever whenever we have multiple capacities in series, we are bound to get second or higher order system. One capacity and one flow, first order. If there is a one capacity, let's say there is a capacity to store the mass and there is a flow of the mass, you will get a first order system. But let's say mass is flowing between two capacities arranged in series, then you will get second order system. Correct? Isn't it? But we should not infer here that if I am saying multiple capacities does not mean that multiple equipment. Sometimes you can have multiple capacities in a single equipment itself. Isn't it? For instance, if you are taking a stir tank reactor, in a stir tank reactor, if you are stir tank heater, let's say, in a stir tank heater, if you are looking at how temperature is dependent on the inlet flow rate. Inlet flow rate I am saying, then it's a second order. Because you will have a capacity to store a mass as well as capacity to store the energy. Both the capacities are there in the same system. So you will get a second order differential equation. Remember, we got the first order differential equation when we are looking at how my temperature is related with the inlet temperature. But if I look at how my temperature in the tank is related to the inlet flow rate, you will get second order. Okay. So what I am trying to say here is multi-capacity does not mean that you need to have multiple equipments in series. You can have multiple capacities in one equipment itself. That is what is. Is it clear to everyone? Now let's analyze these two systems a little bit in more detail. So let's say there are two non-interacting capacities in series. So we are having two non-interacting capacities in series like this, non-interacting. Okay. So what type of differential equation we are expected to get? We will be getting a differential equation like this: tau p1 dy1 by dt plus y1 equals to kp1 f1t, where f1 is the inlet, where f1 is the input, and y1 is the output from the first capacity. Isn't it? Similarly, for the second capacity, let's say the input is y1 and the output is y2. So whatever the output we are getting from the first capacity is given as an input to the second. That is why the output from here, which is y1, is taken as an input here, and the output from the second capacity is y2. Isn't it? And tau p1 and tau p2 are the corresponding time constants. So tau p1 is the time constant of the first capacity, and tau p2 is the time constant for the second capacity. Okay, correct? Is it clear? So tau p1 will be given by what? A1 R1, and tau p2 will be given as A2 R2. Isn't it? In case of tank. Correct? So these are the two capacities in series. Now how we will represent these two systems in the form of block diagram? In the form of block diagram, F1S is the input, and the output is Y1S. So between F1S and Y1S, we will have a first transfer function which is U1S. That will give me Y1S. This Y1S is given as an input to the second system, isn't it? And the output is Y2S, and between Y1S and Y2S, we will have a second transfer function G2S, isn't it? G1S and G2S both will be a first order transfer function. So this will be given by Kp1 divided by tau p1s plus 1, that is G1S, and G2S will be Kp2 divided by tau p2s plus 1. Okay. Now here the example of only two capacities in series is illustrated, but you can have n number of capacities in series. A typical example I said is a distillation part. So let's say if you are having n capacities in series, you can represent them like this. Isn't it? Correct? So now let's look at a very simple case where only two capacities are in series, and each of these capacities are having the transfer function G1s and G2s respectively. Again, we are taking that the G1s and G2s, these are the first order transfer functions, isn't it? So in this case, the overall transfer function G0s, that will be nothing but what? Overall transfer function is nothing but what? The output divided by input, isn't it? So Y2s divided G1s. That is what the overall transfer function will be. So G0s will be given by what? It will be given by G1 into G2, product of the transfer function, isn't it? So in this case, you can see that y2s by f1s will be given by y1s by f1s into y2s by y1s. This y1s, this y1s will get cancelled out. Ultimately, you are going to get transfer function G1s multiplied by G2s. So we can put these two transfer functions here. That is what nothing but G0s. Correct. Now you can see that this is the overall transfer function when I am having two capacities in series. If I look at this particular transfer function, what is the order of denominator here? Order of s in the denominator is 2. So clearly it is a second order system. Clearly it is a second order system. Another conclusion we can draw here is, remember, we can find out how my dynamic response is going to be, whether it is oscillatory, whether it is exponential, whether it is multiple roots at one location, isn't it? All these things we can find out just by finding the location of the roots. I can find out the location of the roots here. Location of the roots comes out to be minus 1 by tau p1 and minus 1 by tau p2. So you can see that whenever I have multiple capacities in series, my roots of the denominator are always going to be negative, real and distinct. Isn't it? Real and distinct, that is what you are going to get. And whenever the roots are real and distinct, what it means? It means you will get the exponential response. You will not get oscillatory response. Oscillatory response you get only and only when your roots are imaginary, and you will not get any imaginary roots here. It is not possible. And that is the reason why multiple capacity processes always give you overdamp system or at max critically damped. They will never give you underdamped. Remember we said we will prove it later, isn't it? Just by looking at the roots here, you can find out that the roots are always going to be real and distinct. You will not get imaginary roots here. And if you don't get the imaginary roots, what it means is you will not get the underdamped system at all. The only possibility here is overdamp or at max critically damped, isn't it? So where we will get a critically damped here? Critically damped. Where we will get the critically damped when this denominator, both the tau p1s plus 1 and tau p2s plus 1 here, tau p1 is same as tau p2, then and then only you will get critically damped. Because critically damped you get when the roots are same. When you have a multiple root, then and then only you get the critically damped, isn't it? So in this case you will get a critically damped only if tau p1 is same as tau p2. So what it means? What is tau p1? Tau p1 in case of tank it is A1R1, isn't it? Similarly tau p2 A2R2, isn't it? So very often the resistance is same, isn't it? Resistance is same. So what it means? Area should be same. That means the tank should be of same size. That is what it means. Okay. That is what it means. So if you are having both the tanks of same size and if the flow resistance is same, then tau p1 is exactly same as tau p2. In that case, you are likely to get critically damped. So you can see that this particular system can give you overdamp system if the size of these two tanks are different. But the size of these two tanks are same, let's say, in that case you get critically damped. You will not get underdamped here at all. You will not get underdamped system here. Yes. Correct? Is it clear to everyone? Yes, no? Okay, so here you can see that if we have this transfer function, then this particular transfer function we can represent in a generalized transfer function, which is nothing but what? Generalized transfer function is given as kt divided by tau square s square 2 theta tau s plus 1. We can represent this transfer function in the form of generalized transfer function and then find out the time constant. So here you can see that tau dash square is given as tau p1 P1 into tau P2. 2 zeta tau dash comes out to be tau P1 plus tau P2, and Kp dash comes out to be Kp1 into Kp2. Okay. Now in this particular equation you can see that you can get equal roots only and only if this tau P1 is exactly same as tau P2. Otherwise not. Okay. How we can solve this? Let's say a step input is given. If a step input is given, in that case, the solution we have already derived earlier. Isn't it? If this is the expression, if the step input of magnitude unity is given, that is f of s is given as 1 by s, then I can find out y to t. Y to t comes out to be kp dash in the bracket 1 plus tau p1 e raised to the power minus t by tau p1 minus tau p2 e raised to the power t by tau p2 divided by tau p2 minus tau p1. So that is what the equation we are expected to get. And this expression we are going to use again and again. Okay. This equation we are going to use again and again. Remember, this expression is valid for overdamped system. This expression is valid for underdamped system. This expression is not valid when I am having critically damped. In case of critically damped, tau p1 is exactly same as tau p2. Then this expression is not valid. Isn't it? Then you get a different expression that you have to derive. That anyway we have derived earlier, if you remember. Let's say if you are having n interacting capacities in series, then this is the expression we are expected to get. And why this expression we are looking at here? There is a reason for that. We will come back to this again when we will look at controller tuning. There are two types of controller tuning: Cohen-Kuhn controller tuning and regular Nichols controller tuning. When we will look at Cohen-Kuhn controller tuning, then we will again come back to this expression one more time. Okay. Remember, most of the chemical processes, they are multiple capacity processes. Distillation column, typically you have 10 to 25 trays, isn't it? Now second order system you can solve easily. But let's say if you are having a system with 10 order 10, is it possible to solve? Difficult. But control में तो हमें solution quickly चाहिए. Because unless and until you solve it quickly, you will not be able to add the manipulation, isn't it? You will not be able to add the external intervention. You have to solve it quickly. So how we can solve this such a generalized expression which is having, let's say, order 10. There is a shortcut to solve this. Okay. And we will again come back when we will look at the controller tuning. There is a shortcut to solve this. Okay. Alright. So we will stop here and we will continue from this point. Tomorrow we will have a class. Tomorrow we will have an online class from 7:30 to 8:30 on Teams. On Teams. ऑनलाइन है भैया, आप मोबाइल से देख लो टीम ऑनलाइन। हाँ और क्या। So tomorrow's class will be online on Teams 7:30 to 8:30 and we will not have a class on Friday. Your attendance will be marked on Teams. Okay.